There is nearly 100 million in your phone and over 1 billion in your computer. The transistor is the most important component in modern electronics. Without it, where would we be? Computers work with bits, and a bit can either be a 1 or a 0, on or off. Now, old computers had manual switches so people could input the 1s and 0s. Now we have transistors to control data, and they are much faster than a person is. Transistors can be used mainly for two things: amplification and switches. They are used in hearing aids to amplify the current coming through it in order to boost the sound, so whomever is wearing it can hear clearly what's going on. Funny enough, one of the first uses for transistors was hearing aids. What happened is that the tiny microphone picked up the sound which will produce an electrical current. Then it was fed through a transistor which will boost the original signal, and then the signal can play through a loudspeaker. Simple really. The other use is switches, and this is what is mainly used in your phone and computer. Just think, in a modern computer chip about the size of your fingernail, there is somewhere between 500 million and 2 billion transistors, and they only weigh 1 × 10⁻30 kilograms. Trust me, that's light. Considering an actual processor can weigh about 40 grams, and that's mainly just the casing and the legs. They work all because of semiconductors. So what they use is silicon, which is commonly found in sand. Now silicon has 4 electrons in its outer shell, 2, 8, then 4, which means that it can bond with 4 more silicon atoms, and it can bond tetrahedrally. This just means that there is a bond on each of the 4 electrons, just like a diamond. Because the electrons are all bonded together, it requires a lot of energy for one to break free. This happens very rarely, and this is why silicon is only a semiconductor. But we can manipulate the silicon so that it will conduct easily. We can do this via doping, which is where you inject a foreign substance into your medium in order to get a better result, in this case better conductivity. There are 2 different kinds of doping. One is called N-type, in which you replace a silicon atom with a phosphorus atom. It works because they're similar size, which means that it will fit into the gap. It also comes with an extra electron. It doesn't affect the overall charge of the material, as there is still the same number of protons as there is electrons, but it means there are more electrons that can roam free throughout the lattice, which means that it will conduct electricity. We can also do P-type doping, which is where you put an atom in that has 1 less electron, like boron. This leaves the boron atom with a gap, so what happens is that an electron can move over to fill in this gap, but then leaves another gap where it was. So we describe this actually as the gap moving rather than the electrons. This will also be neutral for the same reason as before. Now a transistor is made up of 3 of these sections, either PNP or NPN. We are going to focus on an NPN because it is the most common. At one side is the collector, and on the other side is the emitter. In the middle is a base, and it is separated by an oxide layer. Now the important bit happens here, at the NP boundary. What happens is that the positive holes and the electrons will get attracted to each other, and so all the free electrons move from the N to the P side. Then we end up with what we call a depletion layer. There is no free electrons on this side and no free spaces on this side. This actually then gives the P side a negative charge, so all the other electrons are repelled. This means electricity can't flow through the transistor and it is off, or 0. If we then apply a small voltage here on the gate and create a positive plate, this will repel the positive holes on the P side, or attract the electrons. The positive charge is then attracting the electrons on the N side, and providing that the attraction is strong enough, it will overcome the power of the depletion layer, and then the electrons can flow from the collector to the emitter. This is how they act as a switch, because the transistor is now on. The PNP transistor works slightly different. Mainly, it all works backwards. Current will move through it only when there is no current at the base, and it is all about the flow of positive holes through the material. With a PNP transistor, due to the depletion layers, the electrons on the emitter sides move away from the N layer. This then creates a positive region behind the depletion layer, which will then overcome the depletion layer, and electrons can flow into this region. thus leaving a positive area on the N layer. If there is any current here, the electrons in the current will cancel out the positive area and then there will be no current through the transistor. If there isn't, then it forms another positive layer behind the depletion layer, so electrons can flow again, but into the N layer. Then the collector is filled up again from electrons from the power source. So the electrons move in stages, or you could see it as a flow of positive holes from the emitter to the collector. I find PNP transistors harder to get my head round compared to NPN transistors. What is more commonly done is that transistors are actually used in pairs known as a Darlington pair. It is used so the current can actually be amplified enough to be detected by another circuit or microprocessor. This is then often used to power components that require more power than in the circuit, so by amplifying it using a Darlington pair, you can make your component work. Now as transistors are getting smaller, we get some weird effects going on. At the moment, transistors are about 50 atoms across. That is why so many can fit inside your phone and computer. But once we get much closer, the electrons can start behaving quantumly and tunnel their way across the gap, which means that they don't actually work anymore. So this leaves us with a problem, and it is the reason why Moore's law doesn't work after a while. But we are a little far away from that, and they are going to get better for the foreseeable future. So if electrons are starting to behave quantumly, maybe it's time to talk about quantum electronics. The first step towards it is a single atom transistor. The way that it works is by using a base to move an atom in and out of a tiny gap, which will open and close the switch. So, if transistors are going to get this small, computers are going to get a lot more powerful. There are many different kinds of transistors, all of which have different uses. Just for example, the heterojunction bipolar transistor is used for ultra-fast circuits. The nanofluidic transistor is used to move ions through a submicroscopic water-filled channel. A more interesting one is the tri-gate transistor. These have multiple collectors and multiple emitters, and so can do even more. Now for some history. It all started in 1907 when a vacuum tube, or a thermionic triode, was invented. This sent the electronics age propelling forward as it enabled amplified radios and long-distance telecommunications. However, the vacuum tube was easy to break and required a lot of power to run. Physicist Julius Lilienfeld then patented it in Canada in 1925, then in the US in 1926 and again in 1928. However, he never published his findings, nor did he ever have a working prototype according to his patents. Then between the 17th of November 1947 and the 23rd of December 1947, John Bardeen and Walter Brattain performed a series of experiments on a crystal of germanium using two gold point contacts, and what they found is that the output signal was larger than the input signal. William Shockley then saw a lot of potential in this, and obviously there was. If it wasn't for Lilienfeld's patenting of the idea in 1926, Shockley would have then patented it then himself, listing him as the inventor. But this was out of the question due to the patents, and so they started work on a point contact transistor, and in 1956, Shockley, Bardeen and Brattain were awarded the Nobel Prize in Physics for their work on transistors. However, this is when stuff starts to get really interesting. In 1948, two Germans named Herbert Mathieu and Heinrich Welke independently invented the point contact transistor too. However, their transistor produced a more consistent result and was made out of silicon and germanium. Realizing that the three American scientists had already invented it, they rushed into production and used it to improve the French telephone network. However, it wasn't until 1954 when the Americans stole the show again by inventing the modern transistor out of silicon. Obviously, the silicon transistor has a lot of advantage over the old vacuum tubes, such as they don't waste much energy, they are a lot smaller, they require low operating voltages, they have a much higher reliability, they are extremely long-lived, they're sturdier, and they can easily be integrated into any circuit design. So this was the lesson on transistors. Make sure you stick around for the rest of the series all about modern physics. Alright?